This is part 21 in a series of videos in which I'm trying to repair an HP9830A desktop calculator, and this is obviously going to set new records, I think, in the number of installments for this repair. That is really down to the nature of this type of machine and the number of faults that this particular machine has. So far in the previous videos I've repaired a lot of faults, and in the last video I was describing the ROM card and the fact that there appeared to be an issue with the RAM card. What I've done to try and simplify the overall fault finding process is to remove as many of the cards as I can that aren't directly involved with the testing. So far I've replaced the main ROM card, that's this card here. It's basically a drop-in replacement ROM card. The difference is it uses a single more modern EEPROM, and obviously because these are erasable then I can make as many attempts as I want. The other thing I explained in a previous video is that this also gives me the option to write my own code for this machine, and we'll look at that in a few minutes. So in the previous video I said that there was another smaller ROM card in addition to the main ROM card that held the last 512 bytes of ROM, and although it seemed to be working and the decoding seemed to be fine, I don't want to go to the trouble of making a jig specific to read this card because it's a different pinout and configuration from the main card. Also, the main card has the high voltage signal level shifters on it, whereas this doesn't. The level shifters for this are actually on yet another card, and what I wanted to do was eliminate the possibility of either of these being faulty. I have checked them and they seem fine, but the more I can simplify the testing, then obviously the easier it will make life. So what I've done is this monstrosity on the back of the ROM card. It's actually a lot simpler than it looks. It's just a level shifter and inverter. Because the control signals going into the ROMs on the original card are 12 volt signals, I want to obviously reduce that and clamp it down to 5 volts so I don't blow the new ROM card up. So it's just really a inverting buffer and a Xenon resistor to reduce the switching voltage, and this then goes off and connects to the ROM select lines for the additional ROM card, and that means I can now put the entire ROM code into the single EEPROM on the ROM card, and I don't have to worry about whether it's compatible with that particular small ROM card. And also, if I want to change the subroutines in the smaller card, I can just change the code that's in the main ROM. If it works, I'll put it back when I finish the machine, but for now it just simplifies the testing. And so that leads on to the main topic of today's video, which was how to go about testing the RAM card. Now, the HP9830 is a kind of all or nothing machine. It either works or it doesn't, and pretty much anything at all, any fault will stop the machine in its tracks and you won't see anything on the display. Almost every function requires the machine to be working to a fairly high degree. It is a completely discrete processor, which means that there isn't a central processor that's running and then you can kind of branch off from that and carry out specific tests. The core of the machine is a discrete processor, and any faults really anywhere in the machine will trip it up and it won't display anything, it won't respond to keys, and it won't read or write to RAM or ROM properly. The additional problem with this sort of RAM is these are Intel P1103s, and they operate in a bit of a strange way. If you're used to testing RAM devices, then you'd normally put a scope or an analyzer on their outputs and test them that way. You can't do that with these because the signals coming out are actually quite small, and the way they work is these small signals, it's a bit like core memory in a way, where the signals are quite small and the output signals are fed into amplifier detector ICs, and then they are level shifted and turned into digital TTL level outputs. And also, because these are 1-bit devices, there are 4 banks on each card, and it's a 16-bit machine, so 16 of these devices have their outputs used as a single bit in a given word. but the 4 banks are effectively all connected together, which means that you can't individually test the ICs with them in the board because they interact and they all talk to each other. So far I've found a few issues with this. I think there's still an issue on this card with the pre-charged circuits were a bit strange and that's not working. I do have 2 cards with this machine. The other card is in the machine, and today I want to go about testing that. As I said, it's too difficult trying to test these cards using a scope or something like that. So what I've decided to do is to write some code that I can put into the ROM and test the test the card in situ. So in other words, have the machine test the card and see if it can successfully write to and read from the cards. Okay, so the next step was to figure out how to go about doing this testing. Ideally, I'd like to write a program that tests the entire ROM space in one go, which means using pointers and counters. The problem is, of course, to use a counter or a pointer, I need some RAM in the system. And because I don't know if the RAM card's working, I can't just jump straight in and write a program like that, because if it doesn't work, I don't know where the fault is, and it doesn't really get me any further. So going back to the architecture of the machine, the way this writes to and reads from memory is there are 2 cards and each one has a specific purpose. The card closest to the ROM card is the M register card, and it performs a lot of the memory timing, etc., but it also contains the memory address register. That's the register that selects the particular memory address that's being read from or written to, and that's whether it's a RAM card or a ROM card that's being read. So it puts the required memory address into the M register, and then if it's reading data from ROM or RAM, it will read that into the T register card, which is this second card. So I thought the easiest way to write a test program for this, bear in mind I don't want to try and put anything on the display, and when I'm talking about test programs here, I'm not talking about writing programs to run within the 9830 operating system. I'm talking here about machine code programs that run in the absence of the 9830 operating system. So in other words, the only code in the ROM is for the test program, and that way I can do absolute low-level testing on the machine. So I can test the display, the keyboard, etc., all in isolation, one at a time, and that will allow me to fully test each register, the RAM, the ROM, etc., without having to worry about the interaction or various hardware faults stopping the code from running. The first step is to decide how the programs will be formed. So I've written a few test programs so far, and we'll go through these in the video. I'll be fairly brief because I realise these videos are dragging on quite a lot. But the first program is to take a value stored in memory, read it into the A register, which is one of the working registers within the microcode unit, and then save that to a memory location on the RAM card, and then read it back from the memory location into the B register, which is the second working register. And the reason I decided to use different registers is because it allows me to test that they are successfully being updated, and it's not just reading data that's a throw over from something not working properly. In other words, it has to actively read the data to update a different register, rather than us being fooled into thinking it's working just because a register value is not being updated correctly. So the address value I've chosen is 1400. That's an octal address, and that's 300 in hex, which we'll need to know in a few minutes. And the reason I've chosen this address, and also the following test is for the next address location, is this will then give me 2 memory locations in RAM that I can use for a counter to write a program that will test the entire contents of the RAM. But I need to check that these 2 spaces, these 2 RAM addresses are working first, otherwise there is no point me trying to write that program. and possibly if these don't work, what I can do is change these addresses and try and find some part of the RAM that's working, and then use those addresses for my full test program. And then of course that allows me to do a proper RAM test on both boards. This really comes back to what I was saying about the utility of having a new ROM card, that it allows some very thorough testing of the machine. And of course this will be very useful, I hope, to anybody else that's trying to repair one of these or has one that doesn't work, that they'd like to get going. Okay, so the first step, as I said, was to take a value from a ROM address, read it into the A register, write it to a RAM address, read it back from the RAM address into the second working register, and then essentially loop round and do the whole thing again. So I'll get the analyzer started up, point the camera at the screen, and we'll step through and see if it actually works. Okay, so looking at the analyzer, you can see on the trigger screen I'm triggering on the microcode value of EA and the M register address of 0. In other words, we're going to capture instruction fetches from the first memory location if this code runs. In other words, we'll be triggering on this first address, and the way this works, it'll just keep looping around till we've captured some data, and then until I turn the machine off. And what we can do then is look through the analyzer code that we've captured and see if it actually follows what we're expecting. So I'll arm the analyzer, power up the machine. I can turn the machine off now because we've captured the data that we want. And if I now look at the data that we've captured, so if we look at this in conjunction with the code that we're expecting to see, the first instruction that we're going to fetch, bear in mind because this code starts as soon as the HP boots up, then it's going to vector directly to address 0. That's the reset address or reset vector for this machine. And the instruction, that address should be 2000E in hex. Now there are two values here. The inverted one is the value that's actually in the ROMs, but if you remember, that value is inverted when it comes out of the ROM, so this is what we'll see on the analyzer, and these are the values that the machine sees. So as we scroll through, you'll see that the first instruction that's being fetched is indeed 2000E, which is what we expect. And what that instruction will do is it will fetch the value at address E, and it will load that into the A register, and the value at E should be 4 A's. So if we look through, we'll see that the value at E has been fetched, and it is indeed 4 A's. The next instruction will copy that to RAM, so it will now copy that out to the RAM space, and we should see that the address at 300, this is now a RAM space address, so 300, if you recall, is 1400 octal, which is the first byte in RAM. In fact, the RAM starts at 40,000 octal, but because of some odd decoding in the HP, 256 bytes of that, the first 256 bytes, are mapped to 1400 octal, and that's just to make sure that there is some RAM available in the first page, addressable memory page on the machine. It's just more efficient being able to access RAM that way, rather than having to do bank switching every time RAM needs to be read. So in other words, if you have values that need to be used very frequently, then you can access them very quickly. We've written the value 4A's to address 300. The next instruction will read that value back. So it's going to read the value back into register B, and we should see that when we read from that RAM space, we are indeed reading a value of 4 A's. If you go through the microcode sequences, you can go through the microcode disassembly, and that will tell you what each step is actually doing. So if you are interested, you can just make a note of this and see how this microcode relates to what we're actually seeing. But I'm just giving you the summary of what these instructions are doing rather than the detail of how they do it. Okay, so the next instruction at address 3, is to load a value from ROM space F, and that value should be 555, which is this space. This is coming from address 0F, and indeed that's the value it's read into the T register. And if we scroll across, the next instruction should write that to the same memory space that we used before, and as you can see, it's changing that memory address from A's to 555, and then it goes ahead and reads that back, and we are indeed seeing the value we're expecting to of 555. So in other words, we've successfully written complementary values to RAM address 300, and we've read them back successfully and they are correct. This will now just keep looping round, so what we can do is just, if we want to, keep capturing it and making sure that each time it goes round that the values are the same. So I'll start the machine back up, I'll rearm the analyzer, and we should see the values being repeated each time we go around the loop. And so, as we can see, it is successfully reading the same values. And I've run this quite a number of times and it seems to work fine. Okay, so I'll turn the HP off. Now, another thing I mentioned on the design of the ROM card is that there are some bank select switches. And so I now want to run the second test and test the second RAM address, which is of course 1401 or 301 hex. But rather than reprogramming a separate ROM, what I've done is put that code into the second block space in the EEPROM, so I'll now select that with the switch on the board, which I've just done. And if I now rearm the analyzer, power it up, turn it back off, we are now running the second test program. And if we step through this, it's exactly the same as the first, except we're using address 301 rather than 300. So if I scroll through, you can see that we are indeed using address 301, and we're writing values of 4A's to it. We're reading 4A's back from 301. 4 5s are being read, written to the RAM, and then 4 5s are being read back. Okay, so that's the first two tests. That was using the A register, but I decided while I was running these particular tests that I might as well fully test the A and B registers. I've got a second set of test programs. They're identical to the first in the way that they run the test and the values they use. The way they differ is that these tests write from the B register and read into the A register. So in other words, it's flipped the use of the two registers over, and that will allow me to determine if both the A and the B registers are working. Although we read into the B register with the first test, we didn't confirm that that was successful. So this will go a long way to confirming that the B register is actually working. So I'll run through these tests. Okay, so I've run both of these tests and checked through the results on the analyzer, and I am getting the results I was expecting. The values being read back from RAM seem to be correct. And so what I can do now is use those two RAM address spaces for the location of the variables I want in my proper test program, and I can then run that program and do a more thorough RAM test. And once I've got the issue sorted out with the RAM card, then hopefully I can move on and start looking at the rest of the machine. Okay, let me know if you actually want to see that testing. Otherwise I'll just come back when I've got the RAM card up and working, if I can get it working. I don't want to make these videos too long and boring, but if you are interested in seeing some of the process, then please leave a comment.